Hello students, today we will continue sharing the content we are discussing. Today, which is spatial streams and types of radio frequencies, as well as the interference we may encounter in the future. Let's first take a look at spatial streams. Spatial streams are a very important concept in our wireless communication, especially in the application of Wi-Fi and MIMO, multiple input, multiple output technology. Spatial streams refer to the data streams that are sent or received in parallel through antennas in our wireless communication. Each spatial stream represents an independent data transmission path, usually established through different antennas and radio frequency channels. For example, let's assume there is an access point, AP, and a device that supports MIMO technology, such as a computer. So if an AP has two antennas, and the device also has two antennas, then the AP can transmit two independent data streams through these two antennas, making these two data streams spatial streams. If the device and the AP each have more antennas, then more data streams can be transmitted in parallel, thereby improving transmission efficiency and bandwidth. So what is the relationship between spatial streams and the number of antennas? Each antenna supports one spatial stream, which means if your AP has two antennas, it can support a maximum of two spatial streams. If it has four antennas, it can support up to four spatial streams. Importantly, spatial streams depend not only on the number of antennas, but also on the MIMO technology supported by the device. MIMO technology enables the device to transmit multiple data streams simultaneously through multiple antennas, improving the network's transmission efficiency. And what about spatial streams in Wi-Fi 6? They have been further expanded. Wi-Fi 6 supports up to 8 spatial streams in the 5 GHz band, which means that devices can transmit data in parallel through up to 8 independent signal channels. Some high-end APs, for example, Huawei's 8760 series. It has multiple RFs, each capable of providing multiple spatial streams. For instance, the 5 GHz band supports up to 8 spatial streams, while the 2.4 GHz band supports up to 4 spatial streams. Even if an AP has more antennas, such as 16 antennas, the maximum number of spatial streams is still limited by the Wi-Fi standard itself. For example, under the Wi-Fi 6 standard, the 5 GHz band, a single RF supports a maximum of 8 spatial streams. So, how do we achieve multiple spatial streams? How is it implemented? It's through our multi-RF system, which uses multiple RFs, such as the 2.4 GHz and 5 GHz bands, working in parallel. Each RF can support multiple spatial streams, which is why high-end APs can achieve a higher number of spatial streams. For example, 16 spatial streams are distributed across multiple RFs. And then MIMO technology, with multiple input and multiple output, allows these spatial streams to be transmitted in parallel. Each antenna and channel can operate independently, thereby increasing the network's bandwidth and throughput. Next, let's take a look at what single RF, dual RF, and triple RF APs are. AP, which is a wireless access point, has differences in its AP radio frequency and types of radio frequencies, particularly in our working frequency bands and radio frequency configurations. For example, a single radio frequency AP usually refers to a wireless access point that operates on one frequency band. This band it can operate on either the 2.4 GHz band or the 5 GHz band. The characteristic of this type of AP is that it is usually quite simple, suitable for low-density network environments, and relatively low in cost. However, since it can only provide one frequency band, it is limited in terms of bandwidth and spectrum utilization. Its application scenarios are generally suitable for small offices or home networks on environments with lower network demands. And what about dual-band APs? Dual-band APs refer to APs that can operate simultaneously on both the 2.4 GHz and 5 GHz bands. Operating on two bands means it supports two different frequency bands. Therefore, it can provide higher bandwidth and faster transmission rates, allowing devices to connect to both bands simultaneously. Users can choose to connect to the 5 GHz band for greater bandwidth, or the 2.4 GHz band for wider range and stronger penetration. In dense environments, this dual-band AP can effectively manage connections. The two frequency bands enhance network capacity and performance. It is suitable for scenarios like medium-sized offices, schools, or hotels that require network coverage across multiple areas. There is also a tri-band AP. A tri-band AP is equipped with 3 independent radio interfaces by sides, allowing it to operate on 3 bands simultaneously such as 2 5 GHz bands and 1 2.4 GHz band. Or in some cases, all 3 bands could be 5 GHz bands among other configurations, which all fall under tri-band APs. This kind of configuration is typically used in high-density environments, such as large corporate conference rooms or public spaces. In these high-density scenarios, multiple radio frequencies can support more user connections. This reduces signal interference and ensures network stability. Its application scenarios are suitable for places with multiple users, high bandwidth, and the need for simultaneous connections, such as large enterprises, exhibitions, airports, etc., where tri-band APs are used. Then there is the issue of interference, which we often encounter in Wi-Fi networks. First, there is interference from non-Wi-Fi devices. These devices can affect Wi-Fi signals when they use the same frequency as Wi-Fi, such as infrared devices. These are the infrared remote controls and microwaves we use when watching TV. As well as cordless phones, radar, etc., they all operate in the ISM band, especially the 3 mentioned earlier. They mainly operate in the 2.4 GHz band. Why do these devices interfere with Wi-Fi? Although they all operate in the 2.4 GHz band, there are actually distinctions between them. For example, cordless phones or Bluetooth, their interference is relatively small because their power is quite low. We can imagine it like this. The power of our indoor Wi-Fi AP is about 100 milliwatts, while the power of an outdoor AP is 500 milliwatts. However, the power of a microwave oven can be 2,000 watts, which means the signal strength of a microwave oven is 20,000 times stronger than that of Wi-Fi. So, it's like placing a Wi-Fi AP next to a microwave oven. Once the microwave is turned on, the Wi-Fi signal is almost completely overshadowed. This explains why, in some cases, microwave ovens or other high-power devices can severely interfere with Wi-Fi networks. For instance, in a hospital project, the client reported that the Wi-Fi signal was very poor, or even non-existent at certain times. After investigation, it was found that some devices were operating on the 2.4 GHz band and were turned on at specific times, causing the Wi-Fi signal to drop sharply. Therefore, it's important to ensure that Wi-Fi APs are kept away from such devices like microwave ovens, or to adjust the frequency band and power, etc. This is a key to avoiding such interference. In a normal network environment, for example, in a company's Wi-Fi network, when you turn on the Wi-Fi on your phone or computer, all the signals. You see, apart from the network provided by your company. If there are other unfamiliar signals, then these signals are usually considered to be rogue APs. So why are these APs considered rogue? Because they are not provided by the network environment you are in. They might be networks from other places or hotspots set up by individuals. These rogue APs can interfere with your normal network usage, especially when your signal overlaps with the normal network signal. For example, a mobile hotspot is also a form of interference. The signal strength, channel selection, and channel settings of a mobile hotspot are uncontrollable, which can cause conflicts with surrounding Wi-Fi devices. Therefore, the interference from rogue APs and unauthorized devices is something we need to focus on in Wi-Fi. Afterwards, let's take a look at what might appear amidst interference. When mentioning interference, we have to talk about channel utilization. First, it's important to clarify that the concept of channel utilization in WLAN is different from that in the data communication field. In data communication, we often talk about bandwidth utilization, for example, 100 or 1000. Here, the bandwidth utilization is actually 80%, which means 800 megabits, and this is based on the concept of data volume. However, in WLAN, channel utilization is based on the concept of time, referring to the effective data transmission during the transmission cycle. Time ratio. In other words, channel utilization focuses on time, not data volume. It is calculated by dividing the time occupied by effectively transmitted data during the transmission cycle by the total time of the cycle. So it focuses on the network's time utilization rate, not the bandwidth utilization rate. Previously, we mentioned the impact of interference, which is a characteristic of wireless network communication. At the same time, one terminal can only communicate with one AP. For example, cite out Terminal 1 and Terminal 2. When Terminal 1 is communicating with AP1, Terminal 2 cannot simultaneously communicate with another AP. See, this phenomenon might not be noticeable during your daily work because the waiting time is very short, usually on the microsecond level. That is to say, 10 to the power of 6 seconds. So for us, it's almost imperceptible. But in reality, there is a back-off mechanism when devices communicate, meaning there is a brief waiting time when sending data to avoid signal collisions. If interference causes a communication collision, a mechanism similar to CSMA-CD in wired networks is triggered. After a collision, wireless networks use the CA mechanism to reduce the occurrence of collisions. Even so, it is still impossible to completely avoid all collisions, which means that devices will have reduced transmission efficiency due to waiting. Therefore, interference not only causes collisions, but also increases the waiting time between devices, thereby reducing channel utilization. The direct consequence of reduced channel utilization is a decrease in transmission efficiency, which in turn affects the performance of the entire wireless network. Finally, let's take a look at the issue of theoretical speed versus actual speed. After listening, I think everyone should have a significant change in perspective on this topic. First, when purchasing, for example, 802.11n devices, you often see on the packaging 600 megabits or 600 Mbps. Such wording, especially on some wireless routers, will have large 600 megabit signs, giving the impression that you can enjoy 600 megabit bandwidth at home. However, in reality, 600 megabits is just a theoretical speed. In the 2.4 GHz band, it indeed supports a maximum of 600 megabits of bandwidth, but to achieve this speed, several conditions must be met first. The first one is called 4x4 MIMO. This means that your wireless router must support 4x4 MIMO, multiple input, multiple output, and your terminal, such as your phone or computer, must also support 4x4 MIMO technology to achieve the theoretical speed of 600 megabits. Moreover, 600 megabits is a speed achievable under ideal conditions, assuming there is no interference from other devices around. However, in real-world environments, we often encounter some interference, which can slightly reduce performance and speed. These are the main points we wanted to share today. If you are interested in Huawei certification or question banks, feel free to leave a comment below my video. If you have any questions about Huawei's WLAN technology, you can also leave a comment below. I will respond to everyone one by one.